occupants, and by doing this, it will help energy efficiency because people are more accepting about turning off the electrolytes when it's visually comforting.
Yeah.
And so they highlighted 4 of the 19 patterns in this reading, but you can go see all the patterns on their full guide if you would like. But the first one they highlighted on was arranging and choosing the proper furniture. So they showed an office space, and the office space had a bunch of different cubicles and different arrangements, and they showed the room without any furniture, different furniture, and it really changed how it changed the space and how it felt. And then they also talked about, for their second pattern, the like wall to window area ratios, how that plays a role into it because the bigger windows, you know, it increases the lighting and be more bright. And then they showed the difference between just having windows on one wall versus having them on multiple walls in offices, and it made a real difference. So keeping an eye out for the areas. And then they also showed different renderings of like when you use blinds and shades as like controls, you know, so if it gets too bright, like what blinds look like and how that would benefit people and occupants. And then they talked about top lighting and skylights as a pattern, but I feel like that one was like they showed it, but it almost looked similar to electrolytes to me. The images weren't as cool as the other 3, but yeah, using skylights and top lights when able to. But yeah, and then to end the article, they kind of talked about how it's still necessary to do testing. I know we all took lighting design, and when we did those models in the senior lab with the light coming in, it was definitely over process. So testing is still necessary, but the guide is to help point people in a successful direction. But yeah.
Good. Do you have any questions for Madam? Comments? Okay. So I do have a question for you. Testing is very necessary. But if you look at this space downstairs, that's interesting too. I don't believe they did any testing or model simulation, anything. Otherwise, you don't have this problem, right? So you guys will find more problems later downstairs. Let me ask Yosef. Hey, Yosef, can you hear me? Do you have any comments for Madonna? Oh, okay. Actually, I forgot. Let me share my screen, right? Okay, share my screen. I forgot to share my screen. Right now you should be able to see it, right? Did you see it? All right. Yeah, apologize for that. I totally forgot. Okay, so Myron just summarized how can we do a successful daylighting design from furniture arrangement, interior layout, and then gradient material selection and controls, and then how many different types of this daylighting measures we can use, side lighting as a windows, top lighting, or a combined both, and then testing or commission. You see, this is the whole process. And over the entire semester, we will talk about it one by one. Right. So I hope like in the end of this semester, when you guys have a chance to read this article again, you will have a better understanding what they talking about. Okay. Right now it's just like, oh yeah, I agree with that. You did not have very in-depth knowledge yet. Okay, right. So I think that's it. And then I'm going to talk about anything else I need to talk with you. Let me see. Right, I think we are on time. Do you have any questions for course progress or anything? Okay, you're good. All right. So we are going to talk about the slide. Joseph, can you see this slide? Just make sure you can. Can you see? Okay, great. All right. So we are going to talk about the availability of daylight, which is very, very fundamental and also very important. So the daylight availability is actually decided by a few factors that are all summarized here. daylight availability means like how much daylight will come into that space you concern, right? So the size of the location, project location, will be the major concern. For example, if we have a project in say Texas or Phoenix, right? Or another cities on the south side versus you have another project in say Maine state or Michigan, you will have totally different availability of the sunlight coming to your place. Or if you have another project in Seattle, you will say, oh my gosh, you probably don't have much sunlight, right? But you will have a lot of skylight. And the solar position, this one can actually be determined by three: side, day, and time. So side will design solar availability, but on different day or at different time of the day, you have so many different daylight coming to your space, which we understand. In the early morning when the sun rises, the sunlight looks very big and huge, but you actually don't have much sunlight coming to your space. And then when you get the sun rises, over time, you will change the availability of the sunlight coming to your space. Okay. So we will also talk about that. Then on typical day, for example, in summer versus in winter, in fall versus in spring, you will have different daylight availability. So we need to figure out what will be the actual availability by doing the separations. Then sky conditions will be another factor. If you have a heavily cloudy sky, you basically won't have visible sun. So you will have totally different sky distribution and sky availability versus we have a clear sky. Today is actually, it's a little bit foggy today, but the sky looks like it's no cloud. So we may have a sunny day today, right? And the next week, we probably will have different sky conditions. So sky conditions will also affect your daylight availability. And the building orientation, if you have a space with a window facing south versus you have a space with window facing east or west or north, you have totally different daylight availability for that space. Do you still remember the RPC, right? You guys did the project last year. I mean, in the past sprint, we have two windows, right? One is actually facing east, just 3 windows. Another 3 windows facing north. On the east window, will allow the sunlight to come into your space. Sometimes you will see closely and then you will see the sunlight. While the window on the north side, rarely will have some sunlight coming into space, that most of the time it's just light from the sky. So a window facing north is actually the best light source without worry about the delay. For example, we have the Eaton Hall, that computer lab over there with a curved window wall over there. That window wall is facing north, based on my understanding. So you should not see much sunlight coming through that window. Okay. So in the future, if you decide to buy a house and you decide to buy a huge like living with a window wall, and you see a window facing the north, facing the east, facing the other directions, then you need to give it a sun on that. Of course, for residential buildings, you may welcome the sunlight coming to your space instead of like, I want to block the sunlight because I want to use a computer light over there. So it's a different configuration, but different orientations of the buildings will make a huge difference. Even you have the same site, the building model is the same, but if you decide to use a different orientation, you basically will either solve a lot of problems or you create a lot of problems. You have to solve them later. Okay. So when we come to the delineant design stage, the first step is actually to make the orientation of the building facade correct. Because if you made a mistake, you have to spend a lot of money to fix it. So that's the problem. And the local terrain, landscaping, and the nearby buildings, this is like how much reflected daylight come to your space from the nearby surfaces. So they will be decided by the landscape, nearby building facade, trees, building walls, a lot of it, right? Here in Lawrence, we don't have a lot of high-rise buildings, so it's not a big concern like obstructions by nearby buildings. But if you guys haven't been to like New York City, say 5th Street, Times Square, You see, if you have an office over there, you basically don't have the sunlight coming to the office like, for the whole day because the nearby high-rise buildings will block most of the sunlight coming to the space. But that's not the worst of the story. The nearby buildings, they may be glass facade. You actually see a lot of sunlight reflected from the glass facade, they come into your space and produce glare or inner colors. So daylight reflection is actually a important contribution to the daylight availability. But when we decide the building orientations or anything else, we first decide what will be the site and then orientation, and then to which directions the building facade should be based on this orientation. This will also be affected by the nearby and landscape. And we have a tool called a view map to decide. I will show you what to do next, maybe in chapter 3, right? Because we are going to take a photo and then decide to which direction we will have the best solution with that, okay? This slide shows you the solar radiation map. This is not standard data. This is just a data for the United States for that year, annual 2004, which was 20 years ago. And we are not supposed to have a standard solar radiation for every year because it's changed every day, right? So every year you may have a little bit similar but different solar radiation, but this is for the entire United States, and you have the Alaska right here, right? Hawaii right here. So if you look at this, the color bar shows you different values, kilowatt-hour per square meter per day, right, in the unit. So the dark red is has the highest solar radiation, and the brown has the lowest. So if you look at this, which state has the highest solar radiation? Which state? Will that be Kansas? No, Kansas actually is in the middle. So it should be part of California, New Mexico. This one is New Mexico. This is New Mexico. Oh, this is Arizona?
No, sorry.
Okay, Arizona, New Mexico, and a portion of the Texas. Right. You see that Arizona basically have the entire state a lot of solar radiation. That's why if you love to have a lot of sunny days, you should go to those kind of sites. Right? Phoenix, I believe they have the temperature in summer like always above 110, which is horrible, right? And then even in wintertime, I believe the temperature is still going up. Okay. Right. So look at this. You will see, if you are truly interested in the solar energy, you want to use more solar energy, those states need to have the investment with that. And then look at the worst and not the worst, I mean the least solar radiation locations. You will see Seattle, right? And then a few states over there with the dark brown color. Basically, they're always like on the north side, which makes sense, right? And the Kansas is kind of in the middle, again, in the middle. But this is for the annual data. I told you like we are more interested to find the monthly data. So this will just give you the annual data. You will need to find another source for the monthly data. So look at this. We are probably right here. So we probably have a number 4.5 to 5 kilowatt-hour per square meter per day. Okay, this is for a single area per square meter for a single day. Right. And you look at the Alaska. Oh yeah, they have the least solar radiation. I think it makes sense, right? Actually, it's interesting. You see, they have a green spot over there on the north side, and they have the dark brown on the south side. Am I correct? What happened? I guess this might be like they have more sunlight coming to this spot year round, maybe because it's like on top of the north top, so they get some like trace parts of the sunlight from the other side. Yeah. Okay. On Hawaii, surprisingly, they don't have the high intensity solar radiation. I believe just because they are islands inside of the Pacific Ocean, so maybe that affect that. Yeah. Hawaii is actually having the same kind of solar radiation levels as us, which is very surprising to me. Okay. All right, let's go to the next slide. This slide shows you the solar, the daylight zone, right, based on the solar radiation availability. So you see we have zone 1, which has the least solar radiation. A representative city will be Seattle. Okay, look at this. Zone 1 right over there. Zone 1 right over here, here. So those states, those locations have the least solar radiation. And the most solar radiation will be zone 6, right here. Okay. And representative city will be Phoenix. I think it makes sense. Okay. And where are we? We are probably right here. Actually, on the borderline between zone 3 and zone 4. But we shouldn't be in zone 4 because we are in Lawrence right now. We are not in Kansas City, we are in Lawrence. We should be in zone 4. So zone 4, we have a representative city, Los Angeles. Hey, we are having the same solar radiation as Los Angeles. I don't believe we do. But that's for the entire zone, not just for a single city, right? Because if we compare Lawrence with Los Angeles should have more sunny days. Yeah. But this is a representative city for the entire zone. So look at the zone 4 right over there. And then zone 2, right here. I mean, zone 2 right here, right? And zone 3, zone 2 also a portion of it over there. Zone 3 right over there. And the zone 5 here. Zone 4 also have a portion of here. And zone 6 right over there. Zone 4, a portion of the Texas. Right. Oh yeah. So let me ask you a question. This is for United States. If we use the same judging criterion, say zone 1 to zone 6, can you tell me which zone will Canada be? We don't have a map for Canada, but you guys can use your imagination. It might be over there, right? So which zone will Canada be?
1 and 2.
1 and 2 or 3. Right? You see, we have to have a few over there. Right? 1, 2, 3. Will they have zone 6? Never. Right. Okay. Let me tell you a tip to use this map. I sometimes use this map to plan my trip. Say, in summer, I want to go to a cool place. Oh, yeah, I will know which location will be the best. Right? And in winter, I want to go to some hot places. Which place I want to know. So you use different players, no? To plan your trip. Okay, make it useful to you. Okay. So remember, we are in zone 4 for bonus. Right. So, and then solar angle on the sun path. Solar angle on the sun path, we have this kind of phenomenon because our Earth rotates around the sun, and then our Earth is tilted. Okay, that's why we have 4 seasons. Okay, and if you look at the distance from the sun to the Earth, in summer, your distance is actually longer than winter. Hey, wait. In summer, the Earth is actually far away from the sun than the winter. Is that true? Yes, it's true. But why you feel harder in the summer? Because the sun is actually tilted a little bit, so you get more sunlight coming to our location. The Lawrence over there. Okay. And we usually consider 4 days as 4 representative days for the whole year, including 2 equinox days as September 21st and March 21st, spring equinox and fall equinox. And we also have 2 solstice days, including summer, June 21st, and winter, December 21st. So if you do daylighting design or anything related to daylighting, and you want to use a few typical days to do the research, those are the days. So 2 solstice days and 2 equinox days. Okay, let me ask you. January 21st, will it be one of them? We have March 21st, June 21st, September 21st, December 21st. We don't have January. Why I'm asking that question, because I made a mistake in my slides. I put January over there, so I want to correct that. I don't want you to make the same mistake like I made. So that's the reason why we have the sun path and the solar angles change, because the sun path is actually the path to show you where you are. So look at this slide. Say this is a Lawrence, right? And this upper hemisphere is a sky dome. Yeah, you are living here, and you look up, you will see the sky. So you understand, based on your experience of your life, sun will rise from the east, and then gradually moves over time, noon, and then afternoon, and until sunset. Happens all the time, right? And then in summer, your sun will actually be higher. In winter, your sun will be lower, right? So we see this every day. Will it be sometime the sun rises from the west? Okay, never. I mean, I hope that won't happen because the Earth has some problems, huge problems in the end of the line. So look at this. This just tells you how can you find the sun. So for us to find the way the sun, we can use 2 ways. The first way is like, oh yeah, I can tell you where the sun. Say today is September 11th, right? September 11th right now it's 9:34. And the local time, because we are in daylight saving time, the local time is actually 8:34. Okay. So if I tell you the location, I tell you the date, I tell you the time, yeah, you will find exactly the sun position because that's unique for that specific moment, for that specific location. Another way is actually to directly find the solar position. For example, we use 2 angles. We use an azimuth angle. So this is the source, right? The source direction. The azimuth angle is actually an angle of your sun's projected point on the horizon to the true source. Say right now the sun, you have a visual sun. Oh yeah, we should, right? Because we have this over there. So I actually don't see the sun, but let's pretend the sun over there. So right now our true source is over there. So your azimuth angle is actually the same. So you have a projected sun on the horizon, and you just see this angle. That's the azimuth. And then another angle is the altitude angle. That's how high the sun is. So altitude angle is that you look at the sun, and then you have the angles from the horizon to the sun. So that's the altitude angle. So if you know these 2 angles, you know where you sun, right? So the question is like, can you calculate these 2 angles based on the time? Like I told you, September 11th, time is local time is 8:34, right? So you should be able to. The scientists already figured out for you. That's the equations. We just need to practice. So let me go back to this. Solar position, I already talked about this, right? And we have like solar loom, solar. This path is called a solar path, and we have the zenith. A few terms. Zenith is like the upper point straight up, like on the sky, and we have the horizon. We have the geographic location of your site. So those kind of things. Okay, it's very easy to understand. And I also talk about this in winter, your solar path, or sometimes called sun path, your solar path will be this one, which is a little bit lower than your summer. Right? You actually have a different solar path every day. Yeah, it moves like back and forth. So summer, and then go back to the equinox, and then come back to the solstice, and then come back to the equinox again. So it's like moving back and forth every year. Okay, and they can be predicted. Right, so let me show you how can we predict those. So for us to decide where is the sun position of the sun, we have to know a few different terms. So the first one will be the solar altitude and solar azimuth. I will explain to you what is the solar altitude angle, what is the solar azimuth angle, right? But for us to calculate those two angles, we need to know the location of your site. And for Lawrence, I already put it here. So this is for Lawrence, let's say longitude, let's say this is the latitude, this is the longitude. Right? The longitude is west to the east, latitude is north to south. So I always use this because we use these numbers for the acoustic large design, right? Okay. And we have another factor will be the local time, or sometimes called the SeaWorld time. The local time is different from your daylight saving time. Your daylight saving time is 1 hour ahead of your local time right now, and it will be changed back to normal, I believe, in November sometime, November 8th or sometime, right? I don't want them to change. I personally think that they can just fix it, but it's okay, right? And then you have another factor called the local standard meridian. This is a reference angle used for specific time zone. Since we are in time zone central, right? We are in central time zone, right? So we always use nanny. Because this nanny is the longitude differences between our central time zone and Greenwich. What's it called? That's in London, England over there, right? They have a longitude 0. So that's the difference. So we always use NAN. How about if you are in mountain time zone, for example, Colorado, then you use 105. If you are in Pacific zone, you use 120. If you are in Eastern zone, like New York, you use 75. So those angles that for the entire time zone, not just for Lawrence, okay? For the entire time zone. For example, in Pace, Kansas, we also use NAN. Of course, if you want to be very specific, you can use the actual longitude, but this will affect the calculation results. So we still use the standard. That's called the standard meridian. So for us, we are going to use NAN. Okay. And then we have another correction need. That's for the Earth's elliptic orbit, because Earth is not a perfect circle when it moves around the sun. So we have to do the correction, for us to do the prediction of the sun position. Okay. So I already told you the azimuth angle and the altitude angle. So the altitude angle will always be alpha t. So azimuth angle will be alpha s. You can just remember this is altitude t and azimuth s. Yeah, remember that. This is measured from the stars or not. But for us, for building engineers, we always use stars. For other professionals, they always use NORS. But it's very easy to convert. So let me test it, see if you can convert. Right now, it's aimed to the south, right? Let's say the azimuth angle right now is 60 degrees. This is the north. If we convert the angle in light of the reference of north, what will be the azimuth angle? Say if this is 60, what will be this angle? I can actually use my pen to help you draw over there, right? So I think that if I draw on the pan view, it will be easy to understand. Okay. So we have a pan view, right? So we have the this is north, this is south. Right now my sun is right here, projected, okay, and I have my angles. The azimuth angle is the angle, the projected angle between the actual projected line of the sun and the north and the source. I'm sorry. So let's say if this angle is 60 degree, and versus another angle in that of the north, that would be this angle. So what would be the angle for those people not in our field? What do you think?
120.
Yeah, so this will be 120. So if you see the azimuth angle calculated using the online calculator like 120, you will know, oh yeah, it's actually 60 plus. So for that, it's 100. It's actually the same angle. Okay. All right. And then let me show you another slide to show the difference of the azimuth angle and the altitude angle. I explained to you. So whenever you want to find the azimuth angle, you have the sun projected on the ground or horizon, and then you connect that projection of the sun and compare it to the source directions. This angle will be the azimuth. Okay. So the azimuth angle in theory should be from 0 when your sun is actually on the south side to what will be the maximum? Can you predict? Will be maximum 90 or more than? We actually have the sun coming from the back sometimes. Okay. So the actual predictable sun azimuth angle sometimes is larger than 90 degrees. Why? Because on a few days, you actually have the sun. If this is the window facing south, you actually have the sun coming from the back, rises, right? It's not always in front of you. And when the sun sets, sometimes on a few days in fall, in winter, you have the sun actually sets behind you. So we have those angles larger than 90 degrees. Interestingly, pay attention to the polarity of these angles. We have the negative value actually in the morning. We have the positive value in the afternoon. So if you have an angle 60, like I showed you before, we actually need to say it's minus 60. Okay. And this minus or negative 60 does not mean anything other than this is for the morning time. And the positive one will be for the afternoon. Just remember that. So in the future, when you do the calculations, you calculate the sun position in the morning and you get a azimuth angle positive, that means something is wrong. So go back to double check. Okay. Or if you use the north, yeah, they always use minus 20. Then you will, oh yeah, okay. Since it's minus 20, then it will be different. Because for those guys, remember you use the crosswise, right? For those guys, they also use crosswise. So they have the angles like here, 0, north, and they go this way, 90, 180, 270, 360. So for them, there's no negative values. They just range from 0 degree to 360 degree. But for us, since we are using source, we want to make a difference. So we will say our azimuth angle is actually ranging from minus 180 to minus 90 to minus 45 to 0, 45, 90, 135, 180. So that's the okay. Altitude angle is easy to understand and more convenient because this one we're always like positive. Because the sun, if the sun is visible, you should have the sun above the horizon, right? How about if the altitude angle is negative? What happens? The sun is below the horizon. You won't be able to see it. It's probably before the sunrise time, right? So you will calculate the altitude angle as negative angle. In that case, it means it's too early or it's too late. The sun almost sets. In the typical daytime, from sunrise to sunset, your altitude angle should always be positive. Then, let me ask you, what is the maximum altitude angle in this case? Will that be 90 or 180? Yeah, because you never have 90 will be maximum. For example, right now is let's say horizon is 0, summarizes, then you increase 20, 30, 40, 60, 80, 90. And if you keep moving, you will come back, right? You have 85, 80, 75. You won't have like 95, 100, you don't have this kind of angle. So for the altitude, you always have a range from 0 to 9 for visible side, of course. If it's not visible, then of course you will have a different angle. So for the altitude angle, you have a range from 0 to 90 for visible side. For the azimuth, you have an angle range could be from 180 minus degree to positive 180 degree. When you use the south as a reference, if you use the north as a reference, then you have 0 to 360 degree for north. Yeah, makes sense, right? Then let's take a look at the next slide. This one is just the same concept. So this will be the altitude angle. This will be the azimuth angle when you use a true south. Let me test it. Since our south is right here in the bottom direction, so the north is over there, right? And the sun, yeah, that's a little weird. The sun is over there. So this is not for us. This is for Sweden, the southern hemisphere. Okay. In that case, oh yeah, they should use north. Yeah. Because otherwise, the true south angle will be longitudinal 90 degree, and the sun is actually behind us. I mean, we don't see this kind of situation here much. Yeah, right. All right, solar time. Solar time is the time in military time format, like 24 hours. That's exactly the wasted time for the sun in that moment, at that moment. So we calculate solar time using this equation. So solar time is actually determined by your local standard time and your correction of the time using the equation of the time in decimal hours, and then your standard meridian for the size time zone in radius. Remember, for us, we are in the central zone, so we always use 90 degrees, but we have converted to radians. Okay, right. And then the longitude also in radius, and the junior day. This might be a new concept to you. What is a junior day? Junior day is actually we already have the junior day table uploaded to Canvas right here, but I'm going to open from my collection. It's a little bit quicker. So junior day. Oh yeah, actually I have two. So this one has a normal junior day, and then I have my second page is the junior day with leap for the leap year. Yeah, so you can use this one. So this is not a leap year, right? Is this a leap year? It is? Oh, okay, then we check this second. Okay, so junior day is actually the day of the a year starting from 1 to 365. Hopefully, right? We actually have 366 because this is a leap year. So which day is that day? You just check here. For example, today is September 11th, right? September 11th, we are actually 255th day of the year. That's a junior day. Oh my God, it's already 250. That's 2/3 of the year, right? Okay, I cannot imagine because we just passed the summer. So yeah, so when you do the calculation in the equation, you need to put 255 because that's called the junior day. Why people just use junior day for the daily life? I mean, that would be confusing, right? Or maybe not confusing, but it's too inconvenient. Let's say, just a joke. Let's say cancel the month. Just use the junior day. I don't know, not joke, right? People don't do jobs like that. Okay. So to check which day will be the junior day, you just come to this table, right? When you decide it's a leap year, then you check the second table. If it's a normal year, you check the first table. Okay. All right. So let's go back to that slide and then show you the actual equation. We are going to do some practice with that. Okay. That's it. So can we calculate the solar time for today? Let's say maybe 10 o'clock. We don't use 9:52 because that would be too tedious for us to calculate. Let's say 10 o'clock. So we will do the calculation together in class. Solar time, right? So let's do this together. So we first decide the local standard time, SLT, because we have the equation here. So let's just do the equation. So solar time equals to, let me write down here. Solar time equals to the local standard time, LHT, plus your collected equation time, plus 12 times your standard meridian minus your longitude divided by pi. Okay. That's it. So the local standard time, immediate time, because we are 10 o'clock right now, right? So the local time is actually 9 o'clock because we are in the same time. So in this case, this should be 9. Make sense? If you pretend, then we actually take 1 hour again. And then equation of the time. The equation of time is just this equation right here. So look at this equation. We need to know the junior day. We just check the J is 255, right? So junior day J is 255 for today. And that's the only input we need. So you guys do me a favor, calculate the ET based on the unit date 255. See what you will get. Okay. Yosef, if you could, you can also do the calculation over there and just follow up with us. And how much did you get?
0.01.
Yeah, because so the ET 0.10. 10, you have another digit?
105.
105. Okay. That's not because the equation time should be really a fraction of the numbers because we don't have a huge
Oh,
change.
sorry, it was 0.010.
Oh, sorry. 010. So that's 0 here. Okay. Right. Good. And then the next factors we need to put will be the standard meridian for the site location time zone. In this case, it will be 90, right? But we have to convert, because this one should be in radius, we have to convert the 90 to radius. So we use this equation. So radius for 90 will be 90 degree times pi divided by 180. Okay. So this HM, if I do the quick, should be 1.57. Am I correct? Maybe you did a conversion.
Yep.
All right, 1.57. And the local longitude we have in here, 95.2353. So we just do the same 95,2353 times pi divided by 180. So you probably get a little different numbers. One type.
One.
1.66. When you do the math, divided by pi. Okay. Then we got all the input. So you just do the math. ST will be 9 plus 0.0105 plus 12 times these divided by pi. So what is your angles you calculated? Okay. What numbers did you get? Give me more time. Don't worry. Just take your time. 8 what? 8.67 hour. Yeah. So you see your standard sometime is actually a little bit less than your local time. So your local time is just because local time is for the local like large area. The sun is actually for exactly this specific moment. I mean, it's a specific location. So solar time is more accurate, more precise than your local time for the sun. This is like a normal time. This is more like the actual time. Yeah. So you'll see, yeah, we are 3 hours behind the actual local time for the sun. Okay,
So should that number always be smaller than?
And not always, because this is just for us, for Lawrence. We can have a different like coordinates. Say for another side, you may have a little bit more than 9, depends on weighting. It's more like say for the entire like Kansas, because we are in time zone, the same time zone, right? We always use 9 o'clock. But you can imagine like, hey, in Kansas City, because that's the eastern side of the time zone versus the west side of the time zone. We should have different solar times, right? But we always use the same. So this is the actual solar. Did you get it?
Yeah.
So this is more like for specific location. They're very accurate. So if you go to Hayes, they may have 9.2 something. I didn't check it, but I guess maybe. Okay. So that's it. Then this is the exact calculator. Let me make it larger so you guys can see better. You will use it very frequently, right? But I put 2 tablets here. One is for the morning, and one is for the afternoon. You should use the correct one, because if you don't, I will give you an error message. So you will know it's wrong. Okay, so let's use the morning time. Right now, let's see what will be the we just calculated the solar time, right? Where is my solar time? Solar time, ST, right? Solar time. See what will be the solar time. You spend like 10 minutes, no, 10 minutes, 5 minutes calculating. Let me see what we can get. So 255, right? 255 on the equation of the time. You just need to take care of those blue cells. That's the input. Yellow cells will be the calculated numbers. And any white cells is a fixed number, so you don't have to. It's either a fixed number or a calculated number, so you don't have to take care of. So the local standard time, we calculated 9 o'clock, right? What numbers we get? So the solar time right now is 8.58. Close. Okay. I believe this might be more accurate because the equations I used will be a bit more complicated behind this. Okay. Let me see anything else. Yeah, I think that's it. The longitude is actually the same. I use red. The latitude is the same because this is for Lawrence. So you don't need to change the longitude, latitude unless you do a different location. So the solar time is 8.58 hours. Very close. Okay, good. That's a good practice. And then let's do the next practice. How can you calculate the solar azimuth angle? Because these two angles are the angles we actually want to calculate. Solar time is actually a value you want to have in the middle. Unless you truly want to find the solar time, then you can do that. So the solar azimuth angle and altitude angle is actually equation right here. So the azimuth angle is arctangent cosine tau. This one is the solar declination. So you need to calculate these numbers first. And then your T is actually your solar time. That's what you calculated, right? Your solar time. And then cosine sine latitude. Sine tau, that's the solar declination. And then sine latitude, cosine tau, cosine local solar time. So if you look at this equation, you see you actually need to calculate solar time, let's say input, and then the solar declination angle. And then as long as you know your altitude and the longitude, this one actually does not care much about the longitude because it does not need to have the input of the longitude. So you can decide what will be the actual solar azimuth. Okay. Sounds easy, right? But actually very tedious, right? And then the solar altitude angle is this angle, this equation. So you only need the input from latitude on the solar declination angle on the solar time. You already know how to do solar time, right? And then you just need to figure out how to do this. Class practice wise, it will take probably some time, but do you guys want to try? Okay, because these and the take-home assignment will be the only 2 times you guys will do the hands calculation. Yeah. So how about we do the solar declination angle first? So this will be determined by the Julian date. So that's the only input. So you know the Julian date is 270. 55. So you can do the calculation over there. So I'm going to erase the solar time equation here because we don't need this anymore. And then I'm going to keep the solar time on the top. You can just use what you calculate because that's more your time, right? So solar time is 8.67 hours for local time 9 o'clock. And what is the solar declination angle? Have you finished it? What is this angle? Junior day is 255. Yeah, supposed to.
Okay.
Yeah.
Basically 7 times 10 to the negative 7.
7 times 10 to the negative 7. Okay. Okay. You got 0.02. You have a 0.06.
I got
Hey, that's you can even calculate.
I got 0.0212.
0.212. So I will say, since Matt and 80 got similar, we will use 0.0212 or 0.02. And you two double check. Yeah.
Or you know what? I got mine in degrees.
Yeah, mine's in radians.
Mine's in degrees.
Oh, okay. So we are going to use radians, not the degrees, because we need to use radians. Take your time. This one's supposed to be very strong because solar depression means like the correction of the sun tilting.
Okay, I got what Brian got. I got 0.06954.
54 images?
Yeah.
Okay, all right. So we get that one. So we can do this one. Right. So the 0.6954 images. I think this makes sense. Okay. So Joseph, did you get the angles correct? Okay, no problem. Yeah, take your time. Because like I said, this is the only two practices in class for hands calculation. In the future, you can always use either my Excel calculator or you can use the online calculator. So you don't have to deal with this kind of tedious calculation. Right. Then the next one, since we have the solar declination, and we know the latitude, we know the solar time, we know then we can calculate the azimuth and altitude. How about we calculate the azimuth first? The azimuth is this angle, cosine and the radius. When you input the radius, you actually need to be careful because some calculators they input basically for like degree, not radius, right? So you need to do the conversion of that. That depends. Sometimes you calculate different angles because it did not convert the radius to angles or the other way. Right? And then I give you time because this is a little bit tedious. So Joseph, you can also join. It doesn't matter if you give us a different numbers because this is just a practice. You got the numbers? You can tell us, and then no problem.
I got negative 1.53.
Negative 1.53. Is that in degree or in radius? Okay, then convert it to degree. It'll be negative almost. That's supposed to be in degrees.
I don't know. Which one is it?
This since you are doing the arctangent, right? Arctangent is supposed to be in degree, maybe, but it's not correct.
Oh,
It's
wait.
negative.
Hold on. I didn't take the art.
Yeah. Oh, you okay? Okay. Remember, you guys need to calculate. I get a negative.
I got 2.28. I got
2.28. Degree?
Yes.
Negative or
Positive.
okay, then something wrong because like I
Oh,
said,
it's supposed to be?
yeah, because in the morning it's supposed to be negative. Let's go back to the let's go back. Oh, okay, then you can convert to what's your point again? Negative
0.869.
869. Okay, if you convert it to angles, what would be the angle?
I've got something different. That's very
Okay, it's okay. You just practice.
negative 0.966.
6. It's close actually.
I got something in between those two.
Oh, okay. All right. So must be something around this range. Right. So if you look at this chart again, you see for the azimuth angle for the morning time, you always get a negative value if you are using the north. I mean the south, and you will get the positive for the afternoon. So if you calculate azimuth for the morning time, should be negative value. Right. Then since we finished, right, and then let's find the correct answer using the Excel calculator. Okay, I believe we already have the angles calculated over there. So we have 255. So the solar azimuth angle is actually coming from south, negative 66.6 degrees. Okay. And if it's radius, negative 1.1, I'm using the model, right? Negative 1.16 in radius. If it's counted from the north, it should be 130.4. Okay. Good practice. At least you know how to do it. And then for the altitude angle, you just use the other equation. It's similar, right? But the altitude angle is a little bit easier, right? Because this one has, yeah, a little bit similar, but I think I should not say easy, but it's very similar. Yeah. And the altitude angle should be a positive value in this case, because this 10 o'clock is actually 9 o'clock solar time. So you should have the sun visible on the sky. So the altitude angle in this case will be 31.9. Okay. So always use the exact calculator whenever you want to find a quick answer, except for take home assignment number 2, because I actually want you to redo that process again. That's for fundamentals. And in the future, you can always use this one, or you can use some online calculator. The online calculators will always give you the azimuth angle counted from the north. That's the only inconvenience. Yeah, then you have to do the conversion, but I think it'll be easy. Yeah, and the altitude angle will be the same. That's it. I mean, the exact calculator also use almost the same equations over there, you see. But we did more like consistent conversions and everything, so avoid some like manual errors. All right. So I think that's for today because I think that would already give you enough to digest. Right. So next class we will continue work on it, but we will focus more like on the fundamentals. And I will also ask you guys to practice using the Excel calculator. You should have the camera, so you just go there and download, and then take it with you to your vision. Because this is truly something really. Okay, all right. Class dismissed. Joseph, do you have any questions for me? You done?
Recording stopped.
Right. Okay. Of course. Let me. Video assignments. Okay. Right. For the take home. I mean, for the online quiz number 1. Right. So I can share with you. Let me see. Okay. I email you. Or actually, we can go to the commerce. So in chapter 3, I believe, chapter 3, there is bad examples. Did you see that? Did you see my screen? Okay, good. All right. So we are on the same page right now. So we have a few bad examples, and we actually have two. So this one is called the London Sky Crapper, which has some severe problems because of the design. They have some like unwanted reflected solar heat. Okay. So for the first take-home assignment, I want you to read this and then give me a short report to get your points back. For your second online quiz number 2, since you missed it, which is unfortunate because I told the class we have the online quiz number 2 due very soon. I will ask you to do this to make up. Can you go pre-read or read those PowerPoint slides? I just talked about half of them today. And then go read the textbook for the fundamentals, like the azimuth angle, altitude angle, those kind of fundamentals. Read those chapters. And then practice using the Excel calculator, like I showed you on screen today. And then give me a calculation task. Like, can you calculate today or another day you decide? If it's today, like September 11th, let's say 5 o'clock in your like hometown over there. Okay. You still have sun visible at 5 o'clock, right? Do you? Okay, but you can calculate like 5, or maybe you can calculate another time, say 2 o'clock in the afternoon. Just use the Excel calculator and try to get the azimuth angle, altitude angle, and solar time like we did today, and give me like a half-page long answers over there. It's a practice. And then if you did this, I'm sorry. Half page, because you don't, yeah, I mean, I expect that it should be like only half page, but if you need a 1 page, it's okay. For example, if you want to include a picture of your site or anything, it's fine. So give me half page long answers for the calculation using the exact calculator for your site, for your location as a practice. Once you did this, I will get your points back. Okay. We do have, let me see how many assignments, I mean, online quizzes, I'm sorry. Online quizzes, we probably have two more or 3 more. Let me double check. You need to read the syllabus carefully. We introduced the syllabus in the first class. Unfortunately, you were not here. So you need to make up and read the syllabus. So if you look at this, we have a 2 more. We have the online quiz number 3. Did you see that? Which will be due September 23rd. And the online quiz number 4, which will be due October 16th. You won't be able to see them right now because I hide them from you till 1 week before the deadline. Okay. I mean, like for the next 2 online quizzes, can you make sure you will complete them? No, before the due date. No. Each online quiz will have its specific due date. For example, online quiz number 3 will be due September 23rd, right? That will be almost 2 weeks away. 1 to 2 weeks away from today. And the fourth fourth online quiz will be due October 16th. I just want to remind you, this time, in the future, don't miss any more quizzes because I won't be able to give you makeup assignments for those 2 quizzes anymore. Because I think you don't need them. Okay. I will remind the classes every time. For example, I usually will remind my class every class in the beginning, what will be the upcoming deadlines, what they have missed, or any other concerns before the class starts. So if you listen to me carefully, we should be on the same page for everything. I know, yeah, no problem. So for the second makeup assignment, since it will take you some time, I will say, can you give it to me by next Wednesday? Give you 1 week. And for the first makeup quiz assignment, which will be due what time? I give you 1 week before, but I forgot what time. Will that be due Monday? This coming Monday, right? And then just email me, right? Because there is no way for you to upload on Canvas for those answers. When you email me, and then I will give you a grade, and then you will get the points back. Okay. Right, great. So any more questions for me today? No problem. Then I will see you Monday. All right. Bye.